So hi all, my name is Tomasz and today I'm going to talk about libcloud. So first, let's check out what I'll talk about today. First, I'll tell who I am. Then I'm going to tell what the libcloud actually is. Then we are going to look at the reasons why libraries such as libcloud actually exist and why we need them. Later I'm going to tell a bit about libcloud history and the community. And then we'll look at some examples, some code, and we'll also look a bit into the future. What plans do we have for the library? And in the end, there'll be some time for your questions. So, like I said, I'm Tomasz Muros. I work for Rackspace or CloudGeek, where I mostly work on backend stuff. I'm also author of multiple small Python and Django apps, which you can find on my GitHub page. I'm also a huge open source supporter and lover, and I'm one of the around 10 libcloud committers. So what is libcloud? Libcloud is a Python library which abstracts differences between different cloud providers' APIs and exposes all those functionality through a nice and easy to use API, which basically means that libcloud is some kind of abstraction on top of other provider APIs. Some people also call it API glue. I guess, okay, that's a fine name or a fine definition. So it basically, libcloud turns this, you see like a 5 lines of code, into like actual server. So someone once said like cloud is a lie. You run the script, put your credentials in, and you get like an actual server. So one of the reasons why libraries such as libcloud exist is that you can easily choose which provider you use. You're not locked into a single provider. For example, in this case, I used a Rackspace driver. But you see the line with the get driver, you could easily replace this provider Rackspace constant with one of the other 25 or so provider constants, and you would basically get a server at a different provider with basically changing just the provider constant and using different credentials because it's a different provider. So what is the reason, what is the motivation why libraries such as libcloud exist? First of all, cloud standards and all this stuff hasn't actually worked out. There actually are some like 300 or so long PDFs, 300 or so pages long PDF with all the standards, but in practice no one actually uses them. So then we need to have projects such as libclouds which actually allow us to use different providers in practice. So basically we needed some kind of way to standardize all the APIs and provide users and developers an easy to use interface which they can use to interface with many different providers. So the different providers, of course, provide different APIs, which means some of the APIs provide like 5 methods, and for example, you only get 1 method for creating a server, and other providers provide resources in more granular way, which means you first have a 1 method to get a server, and then you also need to call another method to assign an IP address in server and so on. And basically, we abstract all those differences. So you basically call a single method, and you get a server ready to use. And the other reason is different response formats. Basically, as you can see, this is an example of XML. XML is okay. Most of the Python developers don't like it, but it's at least some kind of standard. It's pretty easy to parse it, but so I guess it's okay. Then some other providers like to invent their own format, basically. It's like some text-based format, which is a white space and semicolon delimited. I'm not sure, but some people like to do this. I mean, it's the writing a parser, it's pretty easy, but still, why would you like invent your own standard? Why don't you just use something which already exists? And there are luckily still some providers which use JSON, which is most of us, I assume, prefer JSON, which is easy to use and easy to parse and also easy to read. So another reason is that also different APIs, different providers provide different authentication methods. One of those authentication methods, for example, is shared token. basically you post your API key and username to the provider, and you get back a token, basically some kind of secret which you pass with each request to the provider. So basically this token authenticates you. That's one of the methods. Quite a lot of providers actually use that. For example, Rackspace driver uses this method. The second method of authentication is basically HMAC based. In this case, you use your API key to sign the message. Basically, to create the HMAC hash, you use your API key as a secret. And then you basically pass this signature with each of your requests. Amazon is, for example, one of the providers which use this method. And this method is also a bit tricky because before creating a signature, you actually need to canonicalize all the headers and query strings in your request and sort them before actually creating a signature of this string. So it's actually the authentication code is the code in libcloud which takes the biggest amount of lines. I mean, the rest of the code is actually pretty small, but authentication usually has many edge cases which we need to handle in a transparent way. Third method is also like a pretty simple to use. It's just a basic auth, which means you pass your username, and usually I use API key in the headers. Basically, it's a standard basic auth or digest. And the fourth method, which is actually pretty hard to implement, it's not that standard, is the certificate-based method. For example, one of the providers which uses certificate-based authentication is Microsoft Azure and also EC2. EC2 basically has two APIs. One is like a query string API which we use, which uses HMAC-based authentication, which is kind of simple to use, and the second one is like SOAP API, but no one which, at least most of the people I know who work with Python don't really like SOAP, so we didn't choose this API. So now I'm going to talk a bit about the project. libcloud was originally developed at CloudKick for internal use. CloudKick is a monitoring as a service and server management as a service application, which basically allows you to manage all your servers in a single dashboard. For example, you give us credentials from different providers, and we basically pull all the data about your servers, and you can see and manage all your servers in a single web interface, and you don't need to log into like 5 different sites and so on. And later this year, the project joined Apache Incubator. I'm not sure how many of you are aware of the Apache Incubator, but if you want to become an Apache project, official top-level project, you need to go through the incubator. And the incubator is basically a stage when you need to figure out the licensing issues. You need to show basically the Apache that you know how to manage the community the Apache way, which means by consensus. You also need to get some outside contributors because, like I said, library was originally developed at CloudKick, which is a company, and for a successful Apache project or to get accepted to the top-level project, you need to have multiple independent contributors, which means that not a single company can drive the library in some direction, basically. So you have multiple independent contributors which decide the roadmap of the library. So actually, like in May, we successfully graduated the top-level project, which means now we are like on par with other Apache projects such as web servers, Subversion, and Cassandra, and so on. I mean, the primary reason for joining Apache, or there are more reasons why someone would like to join the Apache Foundation. First is recognition. Many people know Apache, maybe not the Apache Foundation, but people have at least heard of Apache Web Server, which is good. Recognition is always good. Second reason is infrastructure support. So basically you get SVN repository, access to build machine when you can set up, for example, Jenkins, BuildBot, or other continuous integration system, and so on. And the third one is also legal protection. Basically, if someone violates your trademarks and so on, Apache has their own team which handles those kind of issues. And of course, one of the prerequisites for you to joining the Apache or to become a top-level project is that your project is licensed under the Apache 2.0 license. And I'm not sure if you are aware how Apache 2.0 license works, but it's very similar to the BSD or the MIT license, so it's permissive compared to the GPL, which is not. So the libcloud project currently has around 8 active committers, but we also have a lot of outside contributors, which means some people which come, post a patch, and maybe never return back, but we also have quite a lot of active contributors, quite a lot of actually outside contributors which actually come back and stick with the project, which is nice. We also have a pretty active mailing list and IRC channel where we talk about the library and help new users. So now let's take a look at the actual API or how the libcloud is structured. Currently, since the version 5.0, the libcloud has 3 different APIs. First one is Compute API. Compute API allows you to manage cloud servers, or you could call them virtual servers or whatever. Second API, Storage, allows you to manage cloud storage, so services such as Amazon S3 and Rackspace Cloud Files. And the third API allows you to manage load balancers. So load balancers is a service. For example, Amazon provides such service, and GoGrid and Rackspace and some other providers as well. So this is a screenshot which shows some of the providers which we support, which our Compute API support. This is actually now a bit out of date, and we support a few more. So as you can see, we basically support small local providers and also big ones such as Amazon and Rackspace and others. We also have a driver for OpenStack. OpenStack is like a, I don't know if you know Eucalyptus, but Eucalyptus was kind of open cloud platform, but last year Rackspace and NASA joined, and both of them contributed some code, and they created a new project, OpenStack, which is basically open compute platform. So maybe, I don't know, in 5 years, everyone will use OpenStack, and we might not need a libcloud anymore, but that's probably not the case. So first, let's take a look at terminology. Basically, in the Compute API, we have a few terms which we use and which are used through the library, so it's nice to know them. First term is image. Image usually represents an operating system which is installed on your server, but some providers like Amazon also provide a bit more rich interface to the images, which basically means you can use images as templates. You can, for example, pre-install some software on your operating system, on your image, and save this as a template and use this as an image. So instead of like getting a server with the raw operating system, you can already get a server with some stuff installed on it. Second concept in our library is size. Size basically represents your server configuration, which means the CPU, how many CPUs are available to you, how much disk space, how much RAM, and so on. And one interesting property which is nice and you can use, for example, is price. Price attribute allows, if you, for example, with the price attribute allows you to find the cheapest provider among the one we support. For example, you want to have a server with 4 gigs of RAM and, I don't know, 2 gigahertz of CPU, and you can use a bit small list comprehensions to find the cheapest provider which has a server with a size similar to this one available. Because usually providers have some sizes like here predefined, which means you can't like specify, I would want like 2 gigs of RAM, 500 gigabytes of disk, which is kind of sad because cloud actually, with the cloud, providers should provide something like that, because usually with those size concepts, your providers provide some so-called stupid configurations. For example, you have 2 gigabytes of RAM and, I don't know, 2 gigahertz CPU, but you only have 30 gigabytes of disk, which is kind of no sense. And another concept or term is location. Location usually represents a data center or some region in provider. For example, Amazon has multiple regions. One of them is in UK, in United States, Asia, and so on. And the last concept, which is the most important one in the Compute API, is node. We basically refer to servers as nodes. So a node object represents a server. As you can see, it has a name and a public IP and a provider and a lot more other attributes. So the Compute API allows you, like I said, to manage servers, and the base API has a add method, which doesn't sound a lot, but you can actually do quite a lot with these methods. Basically, it has a method to retrieve a list of all the available images, sizes, and so on. But the most important method, or two most important methods, are create node and deploy node. Create node basically allows you to request a server, create a server, and the deploy node allows you to create a server and run some kind of script on it. Basically, we create a server, we call the provider API to create a server, and after we create a server, we SSH to it and run your script. For example, you could provide a script to install your SSH key on the server and to install some kind of software. For example, you could use a script to install Chef or Puppet, which are configuration management tools on the server. And basically, you could use a script to install this, and Chef and Puppet would take care of setting up the actual configuration on your server. For example, setting it up as a web server and so on. And because, like I said, libcloud is an abstraction across many different provider APIs, which means we can only provide a common functionality which works on all the providers. But we also have so-called extension methods, which are prefixed with AX, which allows you to access provider-specific functionality. For example, Amazon EC2 has a concept of elastic IP addresses, and they're the only provider, I think, which has those concepts. And for example, elastic IP addresses, those are IP addresses which you can attach to different servers. For example, this IP address can be attached to server 1, and when you change your mind, you can attach it to server 2. This can be quite useful for load balancing and so on. And for example, only Amazon provides this, and we also provide some extension methods to manage those IP addresses. So this is a simple example which uses the compute API. In this case, I also used Rackspace driver, and it, like I previously said, it installs your SSH key on it, and it also installs Puppet, which is a configuration management tool. So you can see in install key line, there we basically read your public SSH key, and the second line after that, we basically provide a command, because we assume this will be a Ubuntu-based distribution or Debian-based, used apt-get to install Puppet. And then we basically, the last line, we use deploy node. We pass the name of our server image. In this case, I just use the first element of the list, which means it's kind of like lottery. We don't know what size we'll get. Might be like a 256 megabytes node, or might be like 20 gigabytes server with 20 gigabytes of RAM. In any case, we then pass all those arguments to the command, and then our library will do the magic and get you a server with stuff installed on it. Second API which has been added recently is Storage API. Storage API allows you to manage cloud storage, so-called maybe key value storage, because there's usually in cloud storage there's no hierarchy, which means you only have like usually a container, which you can imagine like a folder, and you have an object, which is like a file. And you can't nest, you can't put more containers. You can only have a container and a files in a container, but you can't have a container inside the container. So it's some kind of flat storage. This API is new, so you can see this page is actually pretty empty. Currently, we only have drivers for 2 providers, but it's quite easy to add new ones, so we definitely plan to support a lot more providers later on. So in the storage, we only have 2 important terms. First one is container. Container, like I previously said, represents, you can imagine it as a directory or a folder. Some APIs also refer to containers as buckets, so you maybe heard of this term previously. And we have an object, or so-called file. Object basically represents your file, which is usually a blob, some kind of blob object, but it can also be like a text file. So the storage API has a bit more methods than the compute API, but it's still pretty easy to use. This was our main goal, basically provide common API with its least amount of methods as possible, so basically you can get up and running and playing with it without like reading 10 pages of documentation. You should be able to use it with just looking at the method signatures and so on. In this case, you can see we have a lot of methods for like deleting or creating an object. two more interesting ones are one in italics, so download object and stream and upload object and stream. You probably heard of Python generators, which are a pretty nice concept, and those methods allow you to basically pass in the download object stream. You get back a generator, which means file isn't downloaded to disk and saved locally, but you basically get a generator and you can do whatever you want with it, which means you can like only read the first 500 bytes of file and maybe stream it directly over HTTP, or you can save it to a disk yourself. And here we also have, similar to the Compute API, the extension functionality, which provides or exposes provider-specific functionality. Here is another example. In this example, we use the upload object via stream method. This method, like I previously said, works with streams or so-called generators, or actually iterators, which means this example will directly stream will compress all the files in the path specified in directory variable, and will directly stream this compressed stream to the, in this case, cloud files, so Rackspace Cloud Files provider. This is pretty useful for creating backups because it means that the stream will be directly streamed to the storage provider, which means you don't need to like buffer data on disk, which means you can have only a few gigabytes of free space on disk, but you can actually create a backup of like 50 gigabytes of actual data on disk. So basically just open a sub-process which runs star to compress our directory, and then in the while loop is the actual method which does the upload. So basically pass the iterator to the method which is pipe sdout. Pipe sdout has a read method, which basically you can pass anything which has a read method and return some data to the upload object with stream method. And then basically this gets saved, in this case, to Rackspace Cloud Files. And the last API is the Load Balancer API. This one is also new, has been added in version 5.0, which means, as you can see, it's similar to the Cloud Files. We currently only support 2 providers, but same as with storage, we do plan to support more, and if you want, you can also contribute. If you know someone who provides load balancers, or maybe you provide us functionality, you can come on RSC and we'll help you create a driver for your provider. In the load balancer API, we have 3 so-called important terms. First is the load balancer. The load balancer object represents the actual load balancer instance. So the actual load balancer, which usually listens on a single port and load balances your request. The second term is member. A member represents a server. Usually is a server which is a member of this load balancer, which means the load balancer will balance across all the members. Member is usually important information about the members are just the IP address and the port. And the third term is so-called algorithm. Algorithms specify how load balancer balances the request. First one is random, which just sends a request to the random member. Second one is round robin, which uses round robin algorithm for doing balancing, which means if, for example, if you have 4 servers, first the request will go to server 1, then server 2, then server 3, then server 4, and then server 1, and so on. And the last algorithm is more interesting one. It's list connections, which means the load balancer will redirect the request to the server which currently has the least active connections. Load balancer API is also pretty simple. I think it has altogether like 10 methods. First method is list protocols. Basically, you need to specify a protocol when you provide a load balancer. This is the actual, for example, usually this is HTTP because you balance requests across your HTTP or web servers, and it also has some other methods for like creating a balance and destroying. Attaching balancer attach compute node is one of the interesting one because you can use the node object from the compute API and pass it to this method, and basically in the background we'll just read the node IP address attribute and some other attribute and set up and add this node as a member to the load balancer. And you also have method for detaching and a member, and also for listing members. And same as in the other APIs, we also have methods for accessing provider-specific functionality. Here's a simple example with the load balancer API. In this case, we just create a new balancer. We initially add 2 members with both of them listed on port 8080, which means this could be a HTTP server. Actually, it is because you use protocol HTTP, which means these servers are most likely running the HTTP web application server, and basically with a create balancer call, we create a balancer. In this case, we also use the infinite while loop, where we pull while because usually when you create a load balancer gets created, but it takes a while until it's ready, because it's not like I want a load balancer now. It's usually I want it now, but you actually get it in maybe a few minutes. In this case, we pull because before you can actually do something with the load balancer, it of course needs to come online, which means we need to wait until the state changes to running. Okay, so now let's take a look at plans for the future. As first, like I said, our first goal for the next releases is to provide users with more drivers for the storage and the new load balancer APIs. We also plan to support more services such as DNS as a service, which is also quite a useful service, and there are already many existing providers such as Amazon, Zerigo, and so on. We also plan to support CDN. CDN is kind of related and tied to the storage, so most likely CDN storage will be kind of coupled, which will make it easier to use. And we also plan to explore block storage and maybe even services for monitoring such as server density, CloudGeek, New Relic, and so on. One of our goals for the future is also to improve the pricing data distribution. The setting is that not all of the providers provide APIs for retrieving prices of the servers, which means that we need to check the provider website and save all the pricing data in a JSON file. And we basically distribute this JSON file with each release, which is less than ideal. That's why we plan to provide a better mechanism for distributing this data. Usually it's not a huge problem because providers sadly don't change the prices that often. It might not be a bad idea if they would decrease more often, but anyway. And for the future releases, we also plan to revamp the whole location concept. The problem with location is that different providers expose locations differently. For example, in Amazon, they have like 4 or so locations: United States, UK, Asia, and Europe. And you can use same credentials for all the locations. But with other providers such as Rackspace, different locations are totally separate, and you need to use different credentials for different locations, which makes everything a bit harder and not so easy to use, especially if you usually use one provider, use multiple locations. That's why we want to make it easier. And there are also many other possible improvements. So we also need to tell that we are holding a sprint here on the weekends, so Saturday and Sunday. So if you want to contribute, maybe learn more about the library, you can join us and we'll have fun, maybe even write some code. So that's it. Now it's time if you have any questions.
So what's the difference with Delta Cloud, which is another Apache incubated thing?
Yeah, Delta Cloud is a bit different. Delta Cloud provides functionality over HTTP interface, which should be language agnostic, but we provide a Python library. So their goals are kind of similar, but they expose their interface in a different way. And I think Delta Cloud is also written in Java, if I'm not mistaken.
There are also plans to support Nirvanix.
Sorry?
There are also plans to support Nirvanix.
Support what, sorry?
Nirvanix is a CDN.
Oh, you
cloud.
mean CDN? Yeah, we do
Yeah.
plan to support CDN. But we're mostly, like I said, integrated with storage, which means you'll probably already need to have a storage driver. And
It is a file storage.
oh, okay. Never heard of it.
No, okay.
But yeah, if you know the API, you can like join the sprint or join the RC channel. We'll take a look at it and maybe write a driver.
Maybe a good idea.
Anyone else?
What is the API coverage of for EC2 like services? And my interest is for admin routines and managing images, like registering and so on.
Yeah, our EC2 library does actually have quite a lot of extension methods for managing elastic IP addresses, security groups, and so on. But usually, if you want more provider-specific functionality, you're probably better off using Boto library, which is an Amazon library. But it's actually funny, some users actually do use more provider-specific functionality, but they use libcloud instead of Boto because it's easier to use and it's a lot simpler and it's more fun to work with it.
How do you test all these drivers?
Yeah, that's also a good question. It's not that easy. Currently, we use fixtures. We perform actual testing. We actually hit the provider APIs. We do all those calls, save the responses in a file, and then when we run tests, we load those responses. One of our plans or goals for the future is also to set up like a live testing, basically hitting the actual provider API. But this is hard. It also basically, for example, if the destroy node doesn't work, you'll have a server running, which means someone will need to pay for it. This is a bit harder.
Hi. I just want to ask if you have any plans for supporting Twisted, because I guess it's using the blocking standard library.
Yeah, that's the problem. At CloudKick, when the library was originally developed internally, we also used Twisted a lot. And currently, that's what you usually do if you interface with the blocking API. You use defer to thread, which means the action is executed in a thread pool, which is not ideal, and it also doesn't map nicely to the asynchronous concept. So we did have some previous talk on the mailing list about supporting asynchronous APIs, and we would like to support it, but it's actually, we'll need to refactor quite a lot of the library, which is because it's currently, some of the places are blocking. But going into this direction, refactoring it and supporting asynchronous API is on our roadmap. Okay, thank you.
Thank you.